Alright, so this is the last part of nonlinear optimization. In the last video I was talking about MATLAB built-in functions. We talked about 4 examples. Today we're going to talk about the last example. So in this example we're going to optimize x1 minus 1 raised to the second power and x2 minus 3 squared. Alright, so let's say I have my initial guess here. Lower bound for x1, upper bound, or lower bound, upper bound for x1, lower bound, upper bound for x2. For simplicity, I assume that I do not have any linear inequality. This is basically linear equality. So I leave them blank. I'm using sequential programming. Just to quickly check, yes, I'm using, well, I like to use sequential programming algorithm. And I like to see the function progression as optimization goes on. So I say display iteration. And I'm using fmin constraint optimization. So the arguments are pretty much like as we talked before. The inequality constraints, the equality constraints, the lower bound, upper bound. And now this time I'm saying that I have a nonlinear constraint. So this is the addition to what we covered in the last video. Now, what is this nonlinear constraint? So let's say I'm trying to constrain my optimal solution within a unit circle. Okay. So in passing this function handle unit circle through this at unit disk function. So unit disk is a function that I wrote, and I'm saying that I'm going to introduce this in a minute, and then the options which we talked about here. So let's go down and see what this unit disk is. So unit disk is a function that basically I wrote. It takes the x values, in other words the x and y, or x1 and x2, and then it calculates whether the point x1 and x2 is inside or outside a circle. So this thing is going to be negative if x1 and x2 are inside a unit circle. You can easily test it. Let's say if I put x1 and x2 equal to 0, then this turns out to be negative 1. So this is basically inside the circle, which is right. I mean, x1 and x2 equals 0, and in fact is nothing but the center of the circle. Now on the other side, let's put like x1 like plus infinity and x2 plus infinity, which means we are far in the first quadrant of the Cartesian coordinates. Then plus infinity raised to second power plus infinity raised to second power minus 1 is plus infinity. Okay, so this is positive, which means we're outside the circle. That is true. So this is just to show you how you can test whether you're inside or outside the circle with just 2 examples. Okay, so this is my nonlinear inequality, and I do not have nonlinear equality. So this is basically, I would say, nonlinear inequality. And for the time being, I do not have nonlinear equality. So I just leave it empty. Now, these come out as the output of this unit disk function. Okay. So the first one is going to be the nonlinear inequality. The second one is going to be nonlinear equality. So MATLAB takes these two, incorporate them into this at unit disk, and tries to solve the optimization problem. Alright, the rest of this script is just to visualize what's going on here. I create a mesh for x1 and x2, or for x and y, between minus 5 and 10 with 50 points along each axis. And then I create a mesh grid out of these 2 vectors. So now my capital X and capital Y are basically some matrices, the coordinates of the mesh points. And I'm just trying to plot the function at those grid points. It's the same function x1 minus 1 squared plus y minus 3 squared. It's the same thing here. But I'm trying to basically visualize them on the grid points here. On the grid points x, y. Yeah, okay. And here it is. So we're going to plot the function in 3D. So we're going to plot the surface of x, y, and z. And this is basically for transparency coefficient. We're going to make it a little bit transparent. And that's because if you want to have anything behind or below the surface, we should be able to see it. That's why I put this, transparency coefficient, or alpha. Alright, so now we're going to look at the unit circle. You just want to see where the unit circle is, and I'm going to plot the converged or optimal solution with the black dot. This is to basically view the surface from the top, and the x, y labels, and then the font size of the axes, and then make the unit along each axis equal. Alright, so let's run this code. Alright, so here it is. So this is basically 3D. First of all, if I rotate it, you see that it's a 3D view. It's a bowl shape, you see that. I'm going to rotate it around. It's a bowl shape. But we're looking at the top view only. So this point is the converged solution. My initial guess was 0, 0. And that's what I have it here. Okay, I do not have the initial guess over here presented by any point. So this is only the final point, the converged solution. This black circle is supposed to be red because it's behind the surface. You see that it's behind the surface. You see that red thing? This is the red circle, is a unit circle. Because it's behind it, you would see it as a black line, but in fact it is red. Alright. So I just plotted the unit circle to show that the solution does not go beyond the unit circle because I said so. I said, hey, just find the optimal solution within the unit circle. So my solution better be, within this unit circle. Yeah, so, and then actually, in fact, it is within the unit circle. So, what else I want to talk about here? I think this is it. So now this tells you basically that the solution is optimized. Basically, if I do not constrain it to this unit circle, the minimum should be around here because that's the bottom of the bowl. Right, so these are high mountains here, 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 and here, and actually it goes down as you saw in 3D. You see, if I did the unconstrained optimization, I would get the point right in the middle right here, which is about 1 and 3, if you remember. So x equal to 1. Let's look at that. Yeah. So the minimum of this is going to be 0 at x equal 1, y equal to 3. So x equal 1 is somewhere here, and then that's equal to y 3. Yeah, and that's exactly the center of this circle here. But because I'm constraining to this unit circle, it cannot go beyond that, but it is in that direction. That means if I just remove this unit circle, it's going to converge right in that direction to this point. Alright, so this wraps up the nonlinear optimization in MATLAB. I think we covered a lot of stuff and hope this is useful. Thanks all for watching. Stay tuned for the next video on the numerical solution to differential equations.